Okay, here we're in chapter 5 on linear inequalities and linear programming, and this is section 3 on linear programming in two dimensions, a geometric approach. So, several examples in section 5 are related to a more general type of problem called a linear programming problem. Now, these are mathematical processes that help with decision making. Now, the following detailed example uses an intuitive geometric approach and gives insight that will be helpful when we move to a less intuitive algebraic approach, which is often required for actually solving real-world application problems. So in this example, we have a manufacturer of lightweight mountain tents makes a standard model and an expedition model. Now, each standard tent requires 1 labor hour from the cutting department and 3 labor hours from the assembly department. And each expedition tent requires 2 labor hours from cutting and 4 from the assembly. Now, the maximum labor hours available per day in the cutting and assembly departments are 32 and 84 hours, respectively. Now, if the company makes a profit of $50 on each standard tent and $80 on each expedition tent, how many tents of each type should they make each day to maximize the total daily profit? Now, what we're doing is we're for sure assuming they sell all of the tents that they make. So what is the solution? Well, again, this is an example of a linear programming problem, and we're analyzing the question that indicates the objective of the management is to maximize the profit. So because profits amounts differ for the two types of tents, the management has to decide on how many of each type should be made. And so we have two decision variables. X is going to be the number of standard tents produced per day, and Y is going to be the number of expedition tents produced per day. And then now we can set up kind of a table of what we had, what they kind of told us about all the different ideas and things. So the manufacturing requirements, the objectives, the restrictions are summarized here. So the cutting department gets 1 hour for standard, 2 for expedition, and a total of 32 maximum labor hours per day available. And Standard has 3 for assembly, Expedition has 4, and they have 84 assembly for the assembly department. And then this is the profit per tent. So now what we need to do is we need to create the problem per se. And so first thing is to make the objective function. And in this case, we're making a profit in terms of the decision variable 50 times x, because again, we let x be the number of standard tents and then plus 80 times y. So the amount we make per x tent and amount per y tenths. Now, the form of the objective function suggests the profit can be as large as we like. We just have to make more tents. Now, this is not the case since there are limits imposed by available resources, plant capacity, demand, and so on. And these are called problem constraints. So daily cutting time for X standard tents is going to be added to the daily cutting time for Y expedition tents, and that has to be less than or equal to the maximum labor hours available per day. Same thing for assembly. So we have the cutting and assembly, we have those restrictions we have to follow. And so, again, going back to our writing a problem, we want to maximize the profit. If we make $50 per standard tent, $80 per expedition tent, and we're subject to the constraints, we have 1 hour for X plus 2 hours for Y has to be less than or equal to 32. And here we have 3 times X plus 4 times Y has to be less than 84. So the cutting and the assembly and here, x and y both have to be greater than equal to 0 because we can't have negatives. So we're not going to have negative amounts. So they're always going to be greater than equal to 0. So if we think about that, that's the top right quadrant, quadrant number 1. Now, the graphical solution for this model is outlined on this next slide here. So we basically are just going to plot these lines. And so we plot this one, which is going to be our cutting capacity. This one's going to be our assembly capacity. So those are kind of our upper bounds. And our feasible region is going to be in here because we can't go past those regions because that's our limit of the 84 and 32. And so what we need to do is we need to find each one of these corner points. Okay. Now those corner points are kind of given to you 0, 16, 12, 10, 20, 60, and this is 28, 0. And so those are kind of the key points. And so what we're going to do is we need to choose a production schedule from the feasible region that allows finding the profit using our objective function that we found. And so what we're going to do is we're going to plug in kind of each of these points that are on the feasible region area. And so if we chose 12, 10, we're going to make a profit of 1400. And what we want to do is we want to maximize the profit. So that means it's a maximization problem. So we want to find the maximum value. And so what we're going to do is for each particular p-value, we're going to assign that to the objective function. The resulting plot is given here with parallel constant profit lines. So we kind of see each one of those. Those are the profit lines. And so the optimal solution is the one that has the biggest one. So the biggest one is actually the 1480. What we could have done was we could have plugged in the 016, the 26, and the 280, and the 00, of course, and saw which one gave us the maximum value, and that would be at the 20, 6. And so that's going to give us a profit of $1,480. All right. But what we've done is we've put these lines in here, and so we've solved it for y, and so that's going to give us our profit. And as p increases, basically our y-intercept increases, and the line moves away from the origin. So that's kind of that profit function just moving along here. Now, again, like I said, the maximum profit is when it hits that 20, 6, the optimal solution. And so the profit is maximized at that point. So the manufacturer should make 20 of the standard tints, which is our X, and 6 of the expedition tints, which is our Y, each day to obtain our maximum profit of the $1,480. Okay. Now, the point 26 is called the optimal solution to the problem because it maximizes the objective profit, which is our objective function, and it's in the feasible region. Now, in general, maximum profits occur at one of the corner points, and so the minimum profit, P is equal to 0, occurs at that bottom left corner point of 0, 0. All right, so let's stop with that, and we'll come back for another example.